All right, the last few sections we talked a lot about acids, and so now we're going to switch and talk about bases. So again, bases are something that are going to remove the H plus from the solution. Sometimes they will just bond to the H plus themselves, and sometimes they will produce hydroxide, which then will bond to the H plus to make water and take it out of the solution. So first of all, for strong bases, there's not a list of 6 of them like the acids. The strong bases are just groups 1 and 2, so the alkali metals and the alkaline earth metals bonded to hydroxide. And then you can see because of the acids, all the strong acids are monoprotic, meaning they only have one H that can be donated, except for sulfuric acid, which is a special one that we'll focus on later in this chapter. But for bases, anything in group 2, notice that you have a subscript 2 on the hydroxide because like calcium is +2. And so what that means is it does dissociate completely, but you have to multiply the concentration of hydroxide by 2 because for every compound of calcium hydroxide that breaks apart, you're going to end up with 2 hydroxide ions, and so you have twice the number of particles than you had of the original. So just be real careful and make sure that you multiply that by 2. That's a common mistake that I see. For weak bases, it's really good if you can get to know ammonia. You're going to see that one quite often. This is ammonia, not to be confused with ammonium, ending with an M, which is NH4+. That's a polyatomic ion. So ammonia doesn't have hydroxide, but it will stick to the H+, to form the ammonium polyatomic ion. And therefore, it'll have more hydroxide in the solution, which is going to make a basic solution. We're going to talk about Kb here. So Kb stands for the equilibrium constant of the base, and just like for acids, it's directly related to base strength. So the bigger the Kb, the stronger the base. And in fact, sometimes that's all they do on the AP exam is give you a bunch of bases and a bunch of Kbs and ask you which is the strongest. So again, the bigger the Kb, the stronger the base. And what happens is we're mixing a base with water. The base is going to pull that hydrogen off of water, and we're going to end up with hydroxide in the solution. So that's what's going to make it basic, is this hydroxide right there. And we can write the Kb equation for that. Notice that we're leaving off water because it's a liquid. So if you just do products over reactants, you end up with this. And this is in your reference packet. It's not too hard to figure out, so you don't even need it in the reference packet, but it is in there, which means they're likely to test you on that for the AP exam. All right, this part is really important. When you are solving these icebox problems and you have a conjugate acid-base pair, so for this case we have B and we have BH+, they could either give you the Ka for this, or they could give you the Kb for this. So you just have to be really careful in your icebox. If you literally see hydroxide, make sure that you're looking at the Kb. And if you don't, if you see the H+, then you need to have Ka. And you can easily get one from the other. I'm going to show you that in just a few minutes. To calculate the pH of strong bases, it's just basically the same as before. So if you know the concentration of hydroxide, you can calculate the H+, and then you can get the pH from there. And you can do that from this equation right here. And actually, let's just go ahead and write out, I think it's in your notes later, but Ka times Kb is equal to Kw. So if you ever have, it's kind of hard to read, isn't it? Again, that's a little better. If you ever have one of the K's and you need the other one, you just plug it right into here. And remember, Kw is 10, it's right here, 1 times 10 to the negative 14th. And then there's one more equation that you can use sometimes, and that is this one right here. So sometimes if you have one of the P's and you want the other one, you can just add it to get 14 or subtract it from 14. And I'm going to go through several problems for this chapter. All right, so this is our first example, and it says calculate the pH of a sodium hydroxide solution. So first of all, you need to know that this is strong. It's a group 1 metal bonded to hydroxide, and so that means complete dissociation. So we can assume that it's going to 100% break apart into ions. And we also know that it's a 1-to-1 molar ratio. So as the sodium hydroxide breaks up, it's going to break into sodium and to hydroxide. They're both going to have a concentration of 5 times 10 to the negative 2. Because it's a 1-to-1 mole ratio. And because we have the concentration of hydroxide already, we can just use this to get the pH. So notice that I'm not setting up an icebox for this. You only set up iceboxes for weak things, not for strong things. Strong things, you know that's 100% dissociation, so the original concentration can be used for the concentration of the ions. So now we can say that the POH is equal to the negative log of the concentration of hydroxide. So negative log of 5 times 10 to the negative 2. POH equals 1.3, but be careful, they asked you for the pH. So now we can say that 14 is equal to pH plus POH. So 14 is equal to pH plus 1.3. And pH is equal to 12.7. Let's add a 0 because remember we have 2 sig figs here, and so you need to have 2 decimal places after the pH. All right, let's do one more example with these bases. So this time we're doing this for ammonia, which is a weak base. So if you list your major species, we have a weak base and we have water. And if you compare the weak base's exponent to water's exponent, the ammonia is going to win. So this is going to be more significant. So if it's weak, we're going to set up an icebox. So what we're doing is adding this to water. It's going to pull the hydrogen off water and end up with the hydroxide. So bases don't always bond to that hydrogen, that ion. They also could donate hydroxide, and if they don't have hydroxide themselves, they can pull the H off of water, which will leave behind hydroxide. We're going to ignore water because it's a liquid. And let's see what we got. We have 15 molar here. 0 here, close enough to 0 here, we get a little bit from water. Shift it towards the zeros, and we have 1-to-1 mole ratios. All right, and we are ready to set up our K equation. Now this is Kb. Let's make sure we have hydroxide in the reaction, which we do. So it's okay to use Kb here. And products are the x's, so we'll just say x squared over 15 minus x. We're going to go ahead and make that assumption. And now we can solve for x. Let's check. And the assumption is less than 5%, so we're good. So now we know what x is, and if you go back up here, x is the concentration of hydroxide. So now we can take the POH. And finally, we can do the pH. Watch your sig figs. Make sure you have 2 decimals after that. And that is it for this one.